And we're back with another Cafe Yocto episode featuring the phyCORE-AM62x system module and development kit. Today's video, we're going to be talking about install the SDK or software development kit. Now, what does that mean? Well, in phyText Linux BSPs, the SDK here for the phyCORE-AM62 is going to include a cross-compilation toolchain and a sisters directory, which itself contains headers for your kernel to compile against for your application software. Really, that cross-compilation toolchain is the important bit, and that's going to enable you to compile software on your host machine, which is typically an x86 64-bit architecture, natively running Windows, probably running Ubuntu in a VM. If we compile things there natively, we're going to compile them to run on x86, which is the wrong architecture. Our SOM, the phyCORE-AM62, is a 64-bit ARM architecture, and so you're going to have a file format incompatibility when you compile things natively, and thus a cross-compilation toolchain is required for compiling things on the host to run on the SOM. So we have a couple ways of going about getting the cross-compilation toolchain. This actually ships as essentially a bash script. So you'd run this script, and it's an installer, so it'll set up the SDK for you. We could download it from phyText download server, which I have done myself here, but real quick before we get into using that, I want to just mention, as you iterate your software, let's say you're adding a lot of new features into your kernel, let's say you're porting in drivers, you're going to want to recompile the SDK installer yourself, and that's why we provide steps for building that. For now, if you're just prototyping with the development kit, it's more than likely going to be fine to just use the pre-built. The way this would work if you built it yourself, it's actually covered in our Build the BSP guide here at the very end. Once you've sourced the build environment, along with building the TSDK default image, we could build that toolchain, the SDK, like so. If I ran that, if you pretend that I did that off screen just a bit ago, we can take a look in the deploy directory, here in the SDK directory, and we're going to have that installer built here custom for you. So this one is built myself, but you can just grab the pre-built. So let's do that. Let's go ahead and use the one I've downloaded myself. In order to use that, we're going to have to give it executable permissions, and we're going to have to make a directory to house the SDK once it's installed. So we'll have to actually provide that path to that directory, like so, here in a moment. Here. Give it the SDK directory I just made. And this will just take a little bit to complete.
A few minutes later.
There we go, that completed. Let's take a look at what that's set up here in the SDK directory we made. So we can see a number of new things here, all these files, and then the sisters directory. That's going to contain your kernel headers I mentioned, and other headers from your Linux distribution. The environment setup arch64, so this is what we want to source in order to effectively set up the usage of our compilers that are also contained in here. How do we do that? Well, before I source that environment, let's take a look at our default environment. We do that like so. So this is a bunch of environment variables that are exported whenever you create a new terminal session. I'm just kind of showcasing here because this is the standard list of environment variables. Now watch what happens when I source the environment. Now there's considerably more in here. Some of the important ones I'd like to call out, we can see that the architecture now is being exported to equal ARM64. This variable in particular is actually used when you compile the Linux kernel, or if you set up any application software make files that depend on Arch. Maybe you're supporting your application on multiple architectures. You might be able to select which architecture you're targeting here with this variable. That's how the kernel works. Another one, and then the really important one that we're going to utilize here today is the CC variable. You can see that CC it actually stands for cross-compile, and this is going to point to the cross-compiler included in the sisters directory. And then it's also going to have this flag that's pointing there for other headers from your Linux kernel to compile against. Now, why do I need this again? Well, we already mentioned a little bit. Let's take a look at the native cross-compiler. We can do that with gcc-v. And we can see here that the native compiler on my host is going to target x86, like I mentioned. Now, if we use our new compiler, which we can invoke with this money sign and then -v again, we can see that this guy, the one that we just set up, is now going to target 64-bit ARM architecture. So that's perfect. That's exactly what we want. So let's go ahead and try using this in some simple example. And I like to use Hello World. This is from our Hello World guide, native compilation. This cross-compilation process is outlined here in this guide as well. But I'm just going to use this to steal the Hello World code, populate it into this file. Now, I'm going to first compile it with the native compiler. And remember, I mentioned this is not the way to go. And I'm going to also compile it with my cross-compiler. I'm going to call this one Hello64. Oh, I used the wrong. I hit O. Or 0, I mean. There we go. Fix that. Okay, so now we have these two binaries. We can use this file command to take a look at those. So first, let's look at the natively compiled one. We can see that this is an ELF format, 64-bit, targeting x86, dynamically linked. So all these, all the headers and things, they're going to be linked at runtime on the target. Okay, so yeah, if we tried to run this one here, it would work, and that's expected. But if we try to run the other one, let's take a look at that one real quick. This guy is going to target ARM 64-bit. So if I try to run this, it will not work. It will give me like some file format error, like so. So in order to run this cross-compiled Hello World, we're going to have to transfer it to our phyCORE-AM62x system module. How do we do that? Well, I happen to have it already booted up here. And you can notice too that I have it connected to the network. So I'm just going to grab its IP address, and we're going to SCP that like we did in a previous episode between my cloud-based build server and my local virtual machine. I'm just going to SCP this file to the my target system here, the system module. So we can do that by doing SCP root, give it the IP address, and what file do we want to, oh, I'm doing my arguments backwards. I want to copy the Hello64 architecture binary, and I'm going to copy this to the root directory, like so. Oh, and looks like I have this particular IP address assigned to a different system. And because this is dynamically assigned, this could get reassigned to different systems, right? So it actually tells you how to remove that if this occurs to you. If you're regularly re-updating your SD cards and booting your system module, that host is going to change every time, and it could get that same IP address assigned. So it'll just tell you to remove that known host with this command, and we need to give that a second try here. Easy as that. So if you ever run into that, you know how to fix it. So now if I hop over to my phyCORE-AM62 terminal, we can see that Hello64 is here, and we can run it. Easy peasy. Hello World. And cross-compilation.
That was episode 7 of Cafe Yocto. We will see you guys tomorrow for episode 8. Say bye.